Alright, hello, welcome back. Yet another video about chemistry. Okay, the history of our understanding of the atom. Alright, we're going to start with Dalton. Dalton thought the atom was an indivisible sphere, sort of like a metal BB that you couldn't break apart. He was wrong about that because J.J. Thomson comes along and discovers the electron and develops what's called the plum pudding model. From there, Rutherford comes along and discovers protons in the nucleus, and he creates what's called the sea of electrons model. And then the Bohr model is probably what you were taught in middle school, that the electrons move around the nucleus in energy levels. So we're going to talk about that, and then we'll talk about the modern atom, and we'll go through all of this wave calculation, wave mechanics stuff before we get to the actual real calculations. So, what does the atom really look like? Well, we don't know. The atom is really small, and the problem with looking at anything, if you use any sort of microscope, you're going to need a light source. And atoms are so small that when you hit them with light energy, it actually causes the atom to distort. So what we take a look at is what's called X-ray diffraction, which is a representation of how that atom disturbs an electromagnetic field. So if we were to show that using this sort of construct, this is what the atom would look like. The blues represent areas of negative charge, and the red represents areas of positive charge. But notice it looks more like a wave. It acts like a particle sometimes, it acts like a wave sometimes, but it mainly looks like a wave because this is a wave disturbance that we're actually taking a look at. Alright, so back to our little history of the atom. We talked about Dalton and his indivisible sphere. So what did the Thomson model look like in the late 1800s? Thomson said, look, there's electrons in there, right? Negative charge. So there has to also be positive charge. And so he said that he envisioned that it kind of looked like this. If we look at the Thomson model. He said that we have an atom and it's got these negative electrons, and he said that the negative electrons are scattered throughout the atom, and he said these were sort of like plums in pudding, and so this represents an electron. And then he said the rest of the atom was diffused positive charged material. And he took his inspiration from cellular understanding that you have the organelles floating around in the cytoplasm. So Thomson said, well, it makes sense for the atom too. We're going to have the electrons floating around in this positive cytoplasm-ish type of stuff for the atom. That was wrong. And then later, Rutherford discovered that the positive charge was not diffused, but rather it was it was concentrated in the nucleus. All right, so the Rutherford model is what they call the sea of electrons model, because here's what he theorized. He said you have a positive nucleus, and when they looked at the information for the electrons, they didn't realize this, but since the electrons were moving at 80% of the speed of light, it seems like there were electrons everywhere. And it wasn't that they were everywhere, it's just that they were moving so fast that they appeared to be everywhere. Sort of like a ceiling fan. When you turn it on high, the blades look blurry and they look like a continuous blade, but when you stop the fan, you can see there's actually a lot of empty space in between the fan blades, that it's not an infinite number of blades creating that. But it wasn't a bad idea. It wasn't right. So again, Rutherford, nucleus in the middle, electrons scattered throughout the entire atom, many, many electrons in order to do that. And then Bohr came in and said, look, here's what's happening with those electrons. Those electrons are creating light waves. And if they could create any light wave they wanted to, then we would have a continuous rainbow of colors of light, all the electromagnetic spectrum, not just the visible color, but we would have the entire electromagnetic spectrum of light being produced by these electrons as they move from place to place. As an electron gains energy, it moves further away from the nucleus, and as it loses energy, it returns closer to the nucleus, and this vibration creates light waves. That had been proven already. So Bohr said the fact that hydrogen doesn't show an infinite amount of light shows that there's only certain vibrations that electrons can do. So he said, for instance, there are 2 electrons in what he called the first energy level. So we have energy levels, and then there were 8 more electrons in the second energy level, etc. Right? And what he said was, because he didn't know the nature of it, he theorized that the electrons would move around the nucleus like planets around the sun. The truth of the matter is, they're not found in these energy levels all the time. They're found in there about 90% of the time. So it was a pretty good guess on Bohr's part. The other issue is that we don't know how the electrons move from place to place, but pardon me. What we do know is that they cannot move like planets around the sun. Small particles moving near the speed of light are going to have very different motion than large particles like planets. So one thing we do know is that they cannot move around the nucleus like planets around the sun. But again, this wasn't a bad model for the time period, and it's a model that we teach young people because their brains haven't developed enough to understand the abstract concept of how these things could possibly move. So those are the 3 major changes after Dalton, and then the next major change we're going to talk about in chapter 5. All right, so Bohr based his idea off of light waves being produced. Electrons vibrate and create a light wave. So we're going to review a little bit of wave mechanics. If we have an electromagnetic wave, it is different than a mechanical wave. It does not require a medium to travel through. Another name for electromagnetic waves is light. Now, not all light is visible. We're going to talk about that in a moment. And they're not longitudinal waves. When we talk about electromagnetic waves and moving energy from place to place, we usually draw this diagram. Oopsie poopsie. Let's try this again. I mean, I have a graph here. I should be able to draw this better. Okay, there we go. And a couple of parts of the graph that you should know. First of all, the center of a mechanical wave or a longitudinal wave is called the epicenter. This is called the barycenter. And we said that the highest point or the lowest point, the highest point and lowest point we're going to call the crest of the wave and the trough. And we said this distance from the barycenter to the crest, or from the barycenter to the trough, we're going to call the amplitude of the wave. And that a wavelength represents any position that you start from on a wave to the same exact position on the next wave. So a lot of people like to go crest to crest to get their wavelength. They use the Greek symbol lambda for wavelength. Or some people just write W for wavelength. It's just a variable. But you could get the same distance by going halfway up the first crest to halfway up the second crest. That would also give you wavelength. The time in which it takes for a wave to pass a certain point is called the period of the wave. And the amount of waves that pass per second is called the frequency. All right, so a little review of wave mechanics. Now, electromagnetic waves all move through air and through space at what's called the speed of light. And you do not have to memorize this value. it will be given to you on a test, but 3.0 times 10 to the 8th meters per second is equal to the speed of light. And all waves, speed of light is equal to the wavelength times its frequency. So the Greek symbol lambda stands for wavelength. And this is the Greek symbol mu, which stands for frequency. Now, this is an inverse relationship. In other words, as one thing goes up, the other thing goes down. So if you have a long wavelength, that means you're going to have a very low frequency. If you have a short wavelength, you're going to have a very high frequency. Now, the frequency is related to the energy of the wave. High frequency equals high energy. And low frequency waves have low energy. More of this in the next video when we actually start to apply these equations. Alright, so let's see where we're at. Went over the 3 different types of models after Dalton. Talked about wavelength times frequency gives us the speed of light. And we did our review of wave mechanics. Now, the theory behind the Bohr atom. Bohr said, look, if electrons could be anywhere in the atom, they would vibrate in an infinite variety. And if we look at the visible light spectrum, we would see a continuous rainbow of light, but that's not what Bohr saw. What Bohr saw was only certain bands of light being emitted from hydrogen. And he theorized that if we're only getting certain bands of light, therefore there are only certain specific vibrations that a hydrogen electron can actually create. Now, this had already been proven that when an electron gains energy, it becomes excited, which means it moves away from its what's called the ground state. Now, the ground state is as close as the electron can get to the nucleus without there being repulsive forces interfering with it. And when it absorbs energy, it moves further away from the nucleus into what we call an excited state. So as it moves from ground to excited, it gains energy. And then from excited back to a ground state, it releases energy. And this vibration of going far away and then back towards the nucleus, this constant vibration, is what we call a light wave. The energy produces in the form of a light wave. All right, so the ground state represents the lowest orbital, which means lowest orbit, the lowest area, the area closest. When I say lowest area, I mean lowest in energy, the area closest to the nucleus. And then any other position that's not in the ground state, we call an excited state. And again, since hydrogen only absorbed and released certain wavelengths of light, Bohr was able to say that, hey, there's only certain types of vibrations we can get. So therefore, the electrons have to be in certain positions, which he called orbits. So at the top there, the continuous spectrum, if the electrons were free to move anywhere throughout the atom, that's what we would look at when we refract the light that comes off of the atom. Instead, what we saw was this emission line below, where there were only certain bands of light. Short wavelengths, like purple or blue, there to the left, and long wavelengths, like red and orange, there to the right. So, certain vibrations. Short vibrations would give you the blue light, and then long distances would give you the orange or red light. He said to think of it sort of like an elevator. The electron is normally on the ground floor, but it can get on the first floor. It can get on the elevator and go up to the second floor, or it can stay on the elevator and go up to the 5th floor, and then maybe back to the 3rd floor, and then up to the 6th floor, and then back to the ground state. You have all these different possible combinations of vibrations that you can get. But the electron is not going to get off the elevator in between floors. Now, actually, that's not true. About 10% of the time, the electron does some stuff that we can't really account for. And it actually does get off of the elevator in between these floors, but for now we're going to accept this. And as it turns out, different elements like hydrogen, helium, mercury here in this diagram produce different types of vibrations because they have different number of electrons. So the mercury spectrum and the hydrogen spectrum are very different from each other, and we can use that spectrum in order to identify what type of materials that we're using. Alright, so what do we mean by the entire electromagnetic spectrum, and what do you have to know about it? We're going to do that next. And we're going to use that graph to determine what type of wave that we have based upon its wavelength and its frequency. Alright, so here's an example of the electromagnetic spectrum. Now, at this level, we will give you a copy of this to use on the test. And at the AP level, you would have to kind of memorize not the actual values for the wavelength and the frequency, but you would have to know which ones are the high energy waves and which ones are the low energy waves. Notice the visible spectrum. That is the light that we can see. We cannot detect ultraviolet, X-rays, gamma rays, infrared, microwaves, etc. But they do exist, and they are created by electrons vibrating. As frequency increases, notice as this number here gets larger, this number gets smaller. So, I'm sorry, let me redo that. Undo. This number is also getting smaller. So this number is going up from left to right, and this number is going down because they're an inverse relationship. So if you have a very large frequency, then you have a very short wave, 0.000000000000001 meters. But if you have a very low frequency wave, say 1 vibration per second, then you're looking at a very, very long wavelength. So again, as this value goes down, this value increases. They are inverses of each other. So if you know the one, you can use the speed of light to solve for the other, because we said speed of light is equal to wavelength times frequency. And then we can identify what type of wave that we're dealing with. Last thing I want to conclude with is that there are different types of vibrations. If a vibration ends at energy level 1, in other words, if it starts at 1, goes up to level 2 and then back to 1, or if it starts at 1 and goes up to level 2, 3, 4, 5, 6, and then back down to 1 again, we say that that's part of the Lyman series of vibrations. You cannot see those vibrations. Same thing with energy level 3. If it starts at 3 and goes up to 4 and back, you're not going to be able to see that wavelength. That's what we call, this would be ultraviolet, and this would be infrared, and we are not capable of detecting those type of wavelengths. The ones in the Balmer series, this is your visible light. So the vibrations which you can see created by atoms are those that start at energy level 2, go up to some other energy level, and then back down. So for instance, this 656 would be purple light, and then this 410 would be red, and then this 486 is sort of a yellowish green. So different colors are going to create different wavelengths of light. We can only see the Balmer series of vibrations. We can use this phenomena that certain wavelengths of light are going to be produced to identify materials based upon what's called flame test. Not all materials create a certain color flame, but there are certain ones that are distinctive. For instance, copper is bluish green, and potassium is purple, and strontium is bright red. And I was just having this conversation with my 11-year-old daughter. We're going to talk about fireworks. And again, we're not burning those metals. It's not strontium metal that produces bright red fireworks. It's a strontium salt. So it's the ion. And again, different metal ions in a salt, when you ignite them, are going to give you different colors. So we get our fireworks from that. Alright, so in the next video, we're actually going to do the calculations associated with